Hello everyone, in this video I am going to use the concept of rotating vectors to visualize the addition of oscillations at right angles. So for that we have two oscillations, O1 and O2. O1 has amplitude of 1, frequency of 1 and some initial phase of 0.25. So at t equal to 0 it would translate to this. This is this oscillation. The actual oscillator is here and its representation is this arrow makes an angle of 0.25 radians at t equal to 0, and the second oscillator has an amplitude of 1, frequency of 1 and initial phase of 1.28, and at t equal to 0 it makes an angle of 1.28 radians with a vertical axis, and the actual oscillators moves in this direction. Let us see that as a function of time. This is at t equal to 0. This is the oscillator 1 and this is the oscillator 2. Now in my earlier videos I have explained how to use the rotating vector to describe a simple harmonic oscillator. So we take the projections of these vectors. I'll show this. For example, here for this oscillator the projection of this vector is taken on the x-axis, and that becomes the position of this oscillator with respect to the mean position. And for this oscillator the angle with respect to the y-axis, which is this axis at this time, is taken, and the projection is taken on the vertical axis. The projection is here, and we are looking at what would be the position of an object which is subjected to two such oscillations, and its intersection would be the point. The combined motion is shown in this graph, whose origin is here. This is the x-axis and this is y-axis. So as a function of time it goes like this. Let me put a marker also. So this black dot is the combined motion because of these two motions. So this is the combined motion. So now let us see different cases. In my earlier videos I have shown the same concept using position time graph. I suggest you to go back and look at those. This video is mainly to show how rotating vector is used to describe, how it becomes easier than the earlier description. So at any given time we take the projections of these two vectors. For this oscillator the projection on this axis, remember, and for this oscillator the projection is taken on this axis, and the combined motion is shown in this. So it critically depends on phase difference. So at a phase difference of 1.03, how would the motion look? So let me show. So this is at t equal to 0, and I will mark the positions at different times. So at this instant of time, you can see this is the component because of this vector, this is a component because of this vector, and this is the combined motion. So this would be the path of the combined oscillator motion. So I will put a trace also to remember the line, and I will remove this now dot. So that blue line is the actual path as a function of time. Now let us consider interesting cases. Let us say both the phase difference is 0. When the phase difference is 0, let's see what happens. It's a straight line because both are equal, x is equal to y. Now let us take another interesting case, phase difference of pi by 2. So let us keep the phase of first oscillator same and change the phase of the second oscillator alone. First let us go to t equal to 0. The first oscillator is at the same position, second oscillator the angle has changed, the initial phase, and now let us look at what happens. So there are two color schemes now. One color scheme is to distinguish one oscillator from the other, and the second is to distinguish whether the motion of the combined oscillator is clockwise or anti-clockwise, which is given in red and blue. So when pi by 2, the oscillation would be clockwise and it would be a circle, because the amplitudes are same. So for circle, the amplitudes should be same and the phase difference should be pi by 2. Then the motion would be clockwise. Phase difference of pi. So this is t equal to 0. You can see the phase difference is pi. This makes 0.25 with x-axis. This makes pi plus 0.25 with y-axis. So this is again a straight line, but makes a different angle with the x-axis. Let's go to 3 pi by 2, 4.96. So the phase difference will be 3 pi by 2. The initial phase of the second oscillator is this, while the first oscillator remains same. Let us see what happens. So now see, the motion is counterclockwise and it appears like a circle. Yes, it is a circle. So when angle is phase difference is 3 pi by 2 and amplitudes are equal, it will be counterclockwise. So let us see another case where amplitudes are not equal. Amplitudes are not equal and the phase difference is pi by 2. What happens? So it is an ellipse whose major axis is along the x-axis, because the x-axis amplitude is higher. Or if I take y-axis amplitude higher, t equal to 0. Observe, the vectors have become small and big. So second oscillator is big, so the vector length is bigger than the first oscillator. And again this is an ellipse, but it is a vertical ellipse where the major axis is along the y-axis, because amplitude of second oscillator is larger. So finally let us take some random example to end the simulation and put the amplitudes also equal to make it interesting. So both the amplitudes are equal, frequencies are equal, some random phase difference. Thank you for watching this video.